All right, hello and welcome to the lecture. We are continuing today with chapter 4, sorry, chapter 5. We're on chapter 5 today. And we're continuing with our discussion of redox reactions. Oops. Excuse me. Sorry, my computer is all of a sudden flashing an error. All right, redox reactions. So, just by way of by way of reminder, so we said that redox reactions are reactions in which electrons are exchanged, and that oxidation, when something is oxidized, or when something undergoes oxidation, it means that there is a loss of electrons. You lose electrons when you undergo oxidation, and that reduction was the reverse process, right? When you undergo reduction or are reduced, it involves gaining electrons. And this led us to the mnemonic Leo says Gur, right? Where you lose electrons for oxidation, you gain electrons for reduction. And I gave as an example of a redox reaction at the very end of class on Tuesday. I gave the reaction of hydrogen and oxygen to make water. And we paused for a second because we're like, wait a minute, I don't see electrons changing. I don't see charges changing. How do you know that this is a redox reaction? And that's where we left it. That's the cliffhanger. We said that redox reactions were like drug deals. Someone's buying electrons, someone's selling electrons, but it just looks like normal life is happening, right? It looks like everybody's eating pollos hermanos. So the question is, how do we suss out? How do we figure out who is selling, who's buying? That's our job. And to do that, we need to learn how to assign oxidation states. All right. Now, there are a couple different ways of doing this. There's a couple different systems of assigning oxidation states, and they all work. The method taught in the book is a little lengthy. It involves a lot of different steps and some rote memorization. I'm going to teach a slightly modified version because I believe it's simpler. All right, so I'm going to teach you a 4-step method to assigning oxidation states. The book has a different one. You can use either one. They both will work for you. If you already know the one the book teaches, totally roll with that. There's no point in learning, a different way of doing things. But except for the fact that I think this way is actually easier. So if you've never learned it, I'd recommend doing it this way. But again, as long as you know how to assign oxidation states, that's the important part. All right, so before I tell you how to assign oxidation states, let's start by telling you what an oxidation state is. An oxidation state tells you the amount of charge an element has in a chemical species. All right? It tells you the amount of charge element has in a chemical species. Now, this word species we may not have used before. It is just a generic word that means atom, ion, or molecule. All right, atom, ion, or molecule. That is what species means. All right, now, oxidation states tell you the amount of charge that an element has in a chemical species, even if it's not ionic. So it's a way of figuring out which atoms are electron rich, have a lot of electrons in a given species, which ones are electron poor, which have a lack of electrons. The oxidation states will tell us that. Now, I'm going to give you four steps to assigning oxidation states. All right. So the first rule when it comes to assigning oxidation states is the oxidation state of all atoms must add to the total charge of a species. All right. The oxidation state of all atoms need to add to the total charge of a species. Now, these rules that I'm going to teach you are given to you in order of priority. So you first use rule number 1. Then if 1 doesn't help you, you move to 2. And you try to solve the oxidation states, determine the oxidation states with as little as possible. They're also given to you in priority. This first rule is going to be used in almost every single problem that you do. All right. Now, here's what it allows us to solve problems like the following. So if I asked you, what is the oxidation state of sodium in the species solid sodium? Well, our total charge for this species is 0, and we know that because there's no charge written. So that means the oxidation state of sodium is 0. All right, sodium has an oxidation state of 0 because the total charge on sodium is 0. If I asked you what is the oxidation states of aqueous sodium cations, since we have a total charge of positive 1, the oxidation state of sodium must be positive 1. All right? If I asked you to determine the total charge of hydrogen in a molecule of H2, well, we have a total charge of 0, which means that because we only have hydrogens, the oxidation state of hydrogen must also be 0 in this species. All right, so there's some examples of species that we can determine oxidation states with only the first rule. All right, let's look at rule number 2. Rule number 2 is about hydrogen. Now remember, these are given in terms of priority. So if rule number 1 doesn't help you, you move to rule number 2. All right, rule number 2 says hydrogen is always positive 1 unless, there's a condition here, it is the only nonmetal. All right, then it is negative 1. All right, so hydrogen is always plus 1 unless it's the only nonmetal present. Then it'll be negative 1. Let's do some examples where we assign oxidation states. All right, so okay, so let's look at, for example, water, H2O. Let's assign the oxidation state for every element in water. All right, now rule number one can't help us at the moment. It says that all the oxidation states have to add to the total charge on the species, but we have two different elements present, so it doesn't help us yet. It will in a moment, but not yet. So we move to rule number two. Hydrogen, rule number two tells us hydrogen is always plus one unless it's the only non-metal. So the question is actually going to change my color. Is this a metal or non-metal? Metal or non-metal? And the answer is oxygen. When you look at the periodic table, it is a non-metal. Because it's a non-metal, that means hydrogen is going to have an oxidation state of positive 1. Yep, totally. So oxygen's positive 1. Once we know hydrogen, now we can use rule number 1 to solve for oxygen. Here's how. We know that the oxidation state of our two H's together, right, because there's two hydrogens, plus the oxidation state of our oxygen has to equal the total charge of this molecule, which is 0. All right, we have an oxidation state of 0 for the molecule of water. All right, now we can plug in our oxidation state of hydrogen, which is plus 1, plus the oxidation state of oxygen equals 0. So we have an equation here. 2 times positive 1 is positive 2. 2 plus oxygen is equal to 0. Now, if we want to solve for oxygen, we need to subtract 2 from both sides. And this will give us the oxidation state of oxygen, which is negative 2. So in water, hydrogen is plus 1. Oxygen is negative 2. Let's do another example. Let's do an example. Let's do magnesium hydride. All right, let's assign all our oxidation states. Rule number 1 can't help us yet, so we move to rule number 2, which tells us something about hydrogen. Hydrogen is always plus 1 unless it is the only non-metal. So the question is magnesium a metal or a non-metal? And when you look on the periodic table, magnesium is definitely a metal. So that means that hydrogen will have an oxidation state of negative 1 in this molecule, because hydrogen is the only nonmetal present. So hydrogen has an oxidation state of negative 1. Once we know the oxidation state for hydrogen, we can find the oxidation state for magnesium, because rule number 1 tells us that the oxidation state of magnesium plus the oxidation state of our two hydrogens, of both hydrogens, equals the total charge on our molecule, which is 0. Rock, spot on. It is a metal. So now we substitute in the oxidation state of hydrogen, which for this molecule is negative 1. Right, and that is 0. So magnesium minus 2 equals 0. So now to solve for magnesium, we add 2 to both sides of this equation. And we get positive 2 as the oxidation state for magnesium in magnesium hydride. All right, we're going to do one more example before we move to the third rule, and that is determine the oxidation state for hydrogen in the molecule of H2. Rock, spot on. Magnesium is positive 2. All right, now, whoa. Sorry, cleaning up the board. It's really easy to make a mistake here. You might go, okay, hang on. Hydrogen's always +1 unless it's the only nonmetal. Then it's -1. Hydrogen's the only nonmetal here, so it's -1. You can only skip to rule 2 if rule number 1 doesn't help you. But in this instance, Carolina and Blake, spot on. Rule number 1 tells us that the sum of all our oxidation states have to add to 0. So here we have hydrogen plus hydrogen, oxidation state of hydrogen, plus the oxidation state of hydrogen has to equal 0. So that means 2 times the oxidation state of hydrogen equals 0. And if we divide both sides by 2, we see that hydrogen has an oxidation state of 0. So don't fall into the trap of jumping to rule 2 and skipping rule 1. You always start with rule number 1. If it solves the problem for you, you're done. If it doesn't, you jump to rule 2. If rule 2 can't help you, rule 2 can't help you, you jump to rule 3, which I'm going to introduce right now. So here is rule number 3. When you are assigning oxidation states, metals in the first 2 columns of the periodic table have oxidation states equal to their normal charge. All right, if you have a metal in the first 2 columns of the periodic table, then their oxidation states are equal to their regular ionic charge. Actually, sorry, I put that in the wrong layer. There we go. Oh. There we go. All right. So this allows us to assign oxidation states for problems like the following, or molecules like the following. Let's assign the oxidation states for every element in sodium hydroxide. Rule number 1 can't help us yet. Rule number 2 applies, right? We have hydrogen in play. When you ask the question, is hydrogen the only nonmetal present? The answer is no, because even though there is a metal present, sodium, there's a different nonmetal present, oxygen. So since hydrogen is not the only nonmetal, it picks up an oxidation state of +1. Rule number 3, sodium is in the first column, right, of the periodic table. If you take a look right here, first column of the periodic table, which means that it will take its regular ionic charge. Sodium normally has an ionic charge of +1. So now we, there we go, can assign sodium's oxidation state +1. And now that we only have, once you get it down to one last element where you don't know the oxidation state, then you can apply the first rule. Because now that we know both sodium and hydrogen, we can solve for oxygen's oxidation state, because we know that the sum of all oxidation states must equal the total charge on the species, which sodium hydroxide has a charge of 0. All right? Now, we know sodium's oxidation state, +1. We do not know oxygen's, but we do know hydrogen's, also +1. And this is equal to 0. So if oxygen +2 equals 0, we can solve for oxygen by subtracting 2 from both sides of this equation. Oxygen will then have an oxidation state of -2. All right, let's do another example. Let's assign the oxidation states for every element in calcium chloride. Number 1 can't help us yet. Number 2 doesn't apply at all, right? There's no hydrogen. Number 3, we do have a metal that's in the second column of the periodic table, right? Calcium is right here. Calcium's regular ionic charge is a +2. So calcium is going to have an oxidation state of +2. Now that we know calcium, we can solve for chlorine, because we know that the oxidation state of calcium plus the oxidation state of both chlorines is equal to our total charge, which is 0. Now, calcium has an oxidation state of +2 plus the oxidation state of both chlorines equals our total charge, which is 0. Next, we need to subtract 2 from both sides of this equation. Yep. Carolina, that is exactly correct. So we have 2 times our oxidation state of chlorine is equal to, let me keep my color consistent here, -2. Next, we have to isolate chlorine, so we divide both sides by 2, and we see that chlorine has an oxidation state of -1. All right. So, calcium's +2, chlorine is -1. Those are 2 oxidation states. All right, there's only one last rule you need to learn, and then you can assign the oxidation state to anything I can throw at you. That is rule number 4. And this is the last resort. This is if you can't do it with 1, 2, and 3 combined. This is what you drop to. The most electronegative elements will have an oxidation state equal to its normal charge. All right. The most electronegative element will have an oxidation state equal to its regular ionic charge. That will help us solve problems, assign oxidation states, like the following. Let's assign oxidation states for every element in bisulfate, which is a polyatomic ion. All right. First rule that comes into play is rule number 2, because we have a hydrogen. It's present here with other nonmetals, so it will have a oxidation state of +1. Sulfur and oxygen are not metals in the first 2 columns of the periodic table, so rule 3 doesn't apply. We have to drop here down to rule number 4. When you compare sulfur's position to oxygen's position on the periodic table, oxygen, because it's higher, is more electronegative. So we're going to give oxygen its regular ionic charge, which oxygen's normal ionic charge is a -2. All right, so now that we've used rule number 4 to assign oxygen's oxidation state, we can find sulfur's oxidation state, because rule number 1 says the sum of the oxidation states of all the elements in the species, so the oxidation state of hydrogen plus the oxidation state of sulfur plus the oxidation state of 4 oxygens, is equal to the total charge of the species, which for the first time is not 0. Our total charge here is -1. So we have to put all of these things, set all these things equal to -1. All right, now we know hydrogen's oxidation state is a +1. We have not yet determined sulfur's, but we know oxygen's oxidation state is -2 in this species. And this whole thing is equal to -1. All right, so we have +1 plus sulfur plus 4 times -2, so that's not a positive, is -8 equals -1. So we have 1 minus 8 is -7, right? Sulfur minus 7 equals -1. So we got to solve for sulfur by adding 7 to both sides of this equation. And we see that in this species, sulfur has an oxidation state of +6. So sulfur is +6 in the polyatomic ion bisulfate rocks. You got it. You beat me to it. Let's do a couple more examples. And then we'll get into why we're learning this. All right. We'll get back to that question of who's losing, who's gaining electrons. But first, let's get a couple reps in. Let's determine the oxidation state for every element in a molecule of bromate, which is a polyatomic ion, not one you have to know. Okay, here. Hang on 1 second. Let me throw it back. Carolina, that is a great question. Right, this is the first time. So remember, rule number 1. Oops. Let me open a new slide. Rule number 1 states that all of the oxidation states have to add to the charge of the species. And here, for this molecule, we have hydrogen, sulfur, and 4 oxygen. All those oxidation states have to add to the charge. Now, all the other species that we did had a charge of 0, but this is an ion, so it actually has a charge of -1. That's why we set it to -1. Does that make sense? Yep, the negative sign on top. Exactly. So that's why before there wasn't any charge there, so we just set it to 0. But if there's ever a negative or a positive charge, we have to set our equation equal to whatever that charge is. Totally, yeah. It is a super small detail, very easy to miss, but that's why I wanted to do a few examples so that you wouldn't be surprised when you face this in future testing scenarios. All right, so we've got to figure out the oxidation state of bromine and oxygen. Rule 2 doesn't apply because there's no H's. Rule 3 doesn't apply because there's no metals. We jump straight to rule number 4. And when we compare bromine's position to oxygen, bromine is one space further to the right, oxygen 2 spaces up, so it will break the tie. Oxygen's more electronegative, and its regular ionic charge is -2. So oxygen takes its regular ionic charge for its oxidation state, and now we can solve for bromine because we know that the oxidation state of bromine plus the oxidation state of 3 oxygens is equal to our total charge in this molecule, which is -1. So we have bromine plus 3 times the oxidation state of oxygen, which is -2, equals -1. So bromine minus 6, right? 3 times -2 is -6, equals -1. And now we add 6 to both sides of this equation. So bromine in this ion has an oxidation state of +5. All right, so that is the oxidation state of bromine and oxygen. Let's do one more example. But let's deal with a positive charge. Let's assign all the oxidation states in the polyatomic ion ammonium. All right? Ammonium. Now, hydrogen, rule number 2 applies. Hydrogen's +1 unless it's the only non-metal. Nitrogen is not a metal, so hydrogen is +1. Now that we know hydrogen's oxidation state, we can set up an equation because the oxidation state of our nitrogen plus the oxidation state of our 4 hydrogens has to equal the total charge on this molecule, which is a +1. All right? The only difference between a negative charge and a positive charge is the sign, really. So we have nitrogen plus 4 hydrogens, each with an oxidation state of +1, equals +1, which means that nitrogen plus 4 equals +1. So we can solve for nitrogen by subtracting 4 from both sides of this equation. So the oxidation state for nitrogen in this species is a -3. All right, so that is the oxidation state of hydrogen, the oxidation state of nitrogen. All right. So these are the rules for assigning oxidation states. Again, there's a longer set of them in the textbook. You're more than welcome to use them if they're more familiar. But I think that if you're learning it for the first time, this is the simplest way to do it. There's only 4. It's a lot less to keep track of. Now that we know a little bit about oxidation states, let's revisit that redox reaction that I showed you at the end of last class. The one for the combustion of hydrogen. Now, I've told you this is a redox reaction, right? I told you this is a redox reaction, but again, we don't see any electrons changing hands, so how? We can answer that question, we can finally answer that question using what we know of oxidation states. If you look at hydrogen on the reactant side, the oxidation state of hydrogen is going to be 0 in the molecule H2 because there's no charge and it's the only element present. Same with oxygen. There's no charge, it's the only element present. So the oxidation state of each oxygen atom inside the molecule of O2 is 0. Now watch what happens to each element's oxidation state on the product side of this reaction. Rule number 2 applies to hydrogen, right? It's always +1. It's with a nonmetal, so it's a +1. And then when we solve for oxygen's oxidation state, we already went through assigning oxidation states to the elements in water. So we already know that this comes out to be -2. Now, we've assigned all our oxidation states. If you look at oxygen, oxygen starts at 0 and ends at -2. Has it gained electrons or lost electrons? Ask yourself. Electrons are negative. If you start at 0 and end at -2, you have gained electrons. All right? So we say that oxygen because it's gained electrons, oxygen is reduced. Let's look at hydrogen. All right, hydrogen starts at 0 and ends at +1. So if you've started at 0 and then you end as a positive, have you gained or lost electrons? Well, started at neutral, ended positive, you lost negative charges along the way. So oxygen loses electrons, which means that, hydrogen has lost electrons, which means that hydrogen is oxidized. All right? So hydrogen is oxidized, oxygen is reduced, and that is the exchange of electrons that we did not see in this reaction by just looking at reactants and products. All right? Now, when you ask the question, or when I ask the question, what is oxidized, what is reduced? We're talking about atoms. But let me ask a different question now. So here, I'm just going to clear a little space. All right, so we know that oxygen is reduced. We know that hydrogen is oxidized. Let me ask you a question. In this reaction, what causes the reduction? What causes the reduction to happen in this reaction? And the answer is the molecule H2. That is the reactant reacting with oxygen causing the reduction to occur. Let me ask you another question. In this reaction, what caused the oxidation? All right, what reactant reacts with hydrogen, causing that element to be oxidized? The answer is oxygen. O2, the molecule, causes the oxidation to happen to hydrogen. H2, the molecule, causes the reduction to happen to oxygen. So we say that hydrogen is the reducing agent. Oxygen is the oxidizing agent. All right, hydrogen is the, let me spell it out just for the sake of clarity. Hydrogen is the reducing agent. Oxygen, O2, is the oxidizing agent. All right, so you can have elements. So let's sum up. When you're being asked, there's two ways this question can go. All right, first, when you're being asked, what is reduced? Or when you're being asked, what is oxidized? The answer to both of these questions are atoms. Atoms are elements. You tell them which element is being oxidized, which element is being reduced, and that is the atom or element experiencing the change in oxidation state. Conversely, when you are asked either of these two questions, what is the reducing agent? Or when you're asked what is the oxidizing agent, all right, when you're asked what is the reducing agent, what is the oxidizing agent, the answer to these questions is the reactant that causes oxidation or reduction to occur. All right. So when you're asked what is reduced, what is oxidized, it's the atom or element that's changing oxidation state. When you're asked what is the reducing agent or what is the oxidizing agent, your answer needs to be the reactant that causes the oxidation or reduction to occur. Now we're going to do several problems where we get reps in with these, so it will become more familiar as we do some of these problems. So let's do a few examples. Determine the oxidizing and reducing agents in the following chemical equation. So let's go ahead and start with the reaction between solid calcium and chlorine gas to produce solid calcium chloride. If you are going to determine what your oxidizing and reducing agents are, you first need to assign your oxidation state so you can figure out who's being oxidized and who's being reduced. So all the stuff that we learned leading up to this is going to apply. Let's dive right in. So calcium is going to have an oxidation state of 0 on the reactant side, because it is the only element present in this species and it has a charge of 0. Same can be said for chlorine, right? Oxidation state is 0 on the reactant side. Now for calcium chloride, calcium is a metal in the second row, right? So rule number 3 applies. Its oxidation state is going to be positive 2. And now that we know calcium, we can determine the oxidation state of chlorine because we know that the oxidation state of calcium plus the oxidation state of 2 chlorines will equal our total charge, which for this species is 0. So calcium is positive 2. Chlorine we haven't figured out yet, but they will add to 0. Next we need to subtract 2 from both sides of this equation, which gives us 2 times the oxidation state of chlorine is equal to negative 2. And then we can solve for chlorine by dividing both sides by 2. And this is negative 1. All right. So now that we have the oxidation state for chlorine, let me just rewrite that there. Now we can determine what's oxidized and what's reduced. If we look at chlorine, chlorine starts at 0 and ends at negative 1. So we say that chlorine is reduced. I'm just going to abbreviate it. If we look at calcium, calcium starts at 0, ends at positive 2, so calcium has lost electrons, right? Leo says Gur. So calcium is oxidized. Oops. Carolina, the zeros are the oxidation states at the beginning of the reaction on the reactant side. So calcium starts at 0, chlorine starts at 0, but then they end, calcium ends at +2, chlorine ends at -1. So, all right, so we've determined what's being reduced, chlorine. We've determined what's being oxidized, calcium, but we have not yet determined the oxidizing or reducing agents, all right? The question that we have to ask for chlorine is what causes the reduction? All right, what causes the reduction here? And the answer is calcium is the reactant that reacts with chlorine, causing the reduction. So calcium solid calcium is the reducing agent because it is the reactant that causes chlorine to be reduced. When we ask the same question about calcium, what causes calcium to be oxidized? What reacts with calcium causing the oxidation? The answer is Cl2. Chlorine gas is the reactant that causes the oxidation in calcium. So we say that Cl2 is the oxidizing agent. All right. Cl2 causes the oxidation in calcium, so it is the oxidizing agent. Calcium causes the reduction in chlorine, so it is the reducing agent. Let's do a few more examples. All right. So let's do another example. Let's do, this one's a good one. Let's do the reaction between, yeah, exactly. Oxidating agent or oxidizing agent. There we go. Let's do solid magnesium in its reaction with hydrochloric acid to produce hydrogen gas and magnesium chloride. All right, now let's assign our oxidation states. Magnesium on the reactant side has an oxidation state of 0. In HCl, hydrogen has, so hydrogen is present with a nonmetal, so it's going to have an oxidation state of +1. And then we don't know what chlorine's is, but we can solve for it because we know that the oxidation state of hydrogen plus the oxidation state of chlorine equals our total charge, which is 0. So hydrogen is +1 plus chlorine equals 0. And now we can solve for chlorine by subtracting 1 from both sides of this equation to give us chlorine has an oxidation state of -1. So H is +1, Cl is -1. All right, now hydrogen on the product side is a 0. Magnesium is in magnesium chloride. Here it is, rule number 3 is going to help us out. It is a metal Um, and in the second column of the periodic table, so its regular ionic charge is positive 2. And now we can solve for chlorine's oxidation state, because we know that the oxidation state of magnesium plus the oxidation state of 2 chlorines equals our total charge, which is 0. Magnesium has a charge of plus 2 chlorides equals 0. And now, let's see, we subtract 2 from both sides of this equation to isolate chlorine on one side. So 2 times chlorine is equal to negative 2. And then we divide both sides by 2 to find chlorine's oxidation state, which again is negative 1. So chlorine in the molecule magnesium chloride has an oxidation state of negative 1. All right, so we have now assigned all of our oxidation states. Now we need to determine what's being oxidized and what's being reduced. One of the things you'll notice is that magnesium, so when you're doing this, you want to look for the elements that are changing. Magnesium starts at 0, ends at positive 2. So is magnesium, definitely we have a change in oxidation state. The question is it losing or gaining electrons? Well, it starts at 0. It ends at positive 2. So that means if it's gone from 0 to positive 2, it's lost electrons. That means it has been oxidized. Leo says good. Leo is lose electrons, oxidation. So magnesium is oxidized. Looking for another element who's experiencing a change in oxidation state. Hydrogen jumps out. It starts at positive 1, ends at 0. So hydrogen experiences a change in oxidation state. And rocks, you nailed it. It is losing electrons. Right, so hydrogen starts at a, hydrogen starts at a positive 1 and ends at 0. It has lost positive charge, but that means it's gained negative charge. Remember, electrons are negative. So if it starts at a positive and ends at a negative, it's gained ends at 0, it's gained negative charges. It's gained electrons. And gaining electrons means your reduction. Remember, Leo says Gur. Gur is gain electrons reduction. So hydrogen is reduced. Yes, it gained 1 electron. Exactly. Now you might be looking at this and going, well, what about chlorine then? What's chloride in this? And chloride is nothing, because chloride experiences no change. So we can ignore it. All right? Chloride experiences no change, so it's not a part of the reduction or oxidation in this reaction. It's a non-player. All right, so because magnesium is oxidized, the question is, what reactant causes that oxidation? And the answer is aqueous HCl reacts with magnesium to cause the oxidation. So HCl, hydrochloric acid, is the oxidizing agent. When we look at, we know that hydrogen is being reduced. When we ask what reacts with hydrogen to cause the reduction, the answer is solid magnesium. Solid magnesium reacts with HCl to cause the reduction. So magnesium metal is the reducing agent. All right. Oxidizing agent, reducing agent. All right. For the sake of time, I'm going to move on, but I'm going to leave you with 2 problems to try on your own. So this is just for your own fun. Problems the same, determine the oxidizing agent, reducing agent for these 2 reactions. One is the reaction of ammonia, gas with oxygen gas to produce nitrogen dioxide gas and water vapor. And the second reaction is a decomposition reaction. The decomposition of HI to produce H2 and I2. So you can try these on your own. For practice. All right, but I'm going to press on in lecture. All right, to our next topic. All right, so the next topic that we have to cover is called stoichiometry. All right, stoichiometry. And I have to issue a caveat emptor for this topic. Caveat emptor is a Latin expression, and it means buyers beware. The reason why I'm giving you this warning is because stoichiometry might be the hardest subject in this class. It is for a lot of students, in my experience. I've been teaching college chemistry for the past 7 years, and this is the thing that students tend to struggle with the most. So this might be the hardest topic. It is for many students. But on top of it, it also might be the most important topic. In this class. So that means once we start doing stoichiometry, we never really stop. This is going to be with us till the end of the semester. So the warning that I'm giving you is basically you got to get good at this. It's the most important thing we're going to cover this semester, especially if you have any future chemistry. If you're planning on taking more chemistry, you're going to be doing just loads of this. I was teaching earlier this morning, I was teaching an organic chemistry lab for Sacramento State. And my students had questions about stoichiometry because it still comes up, all right, even in that advanced level of a class. So what we're about to learn, what we're about to go over, will be with you to the end of your chemistry career, however long or short that is. But at the very shortest, you're going to have to be good at this when you take the final exam in this class. So, anyways, this is something you really want to focus on, you really want to master, because it's very important to at least your success this semester. All right, with all of that rhetoric laid down, what is stoichiometry? Well, every conversation about stoichiometry begins with a conversation about the mole. And I'm not talking about a blind burrowing mammal. So if you want a good time, Google image search star-nosed mole. It's like a mole with a nose that has like octopus tentacles on it. It's really weird. It's super cool. They feel around. The tentacles feel around as it moves underground. It's pretty cool. So Google star-nosed mole if you're bored this weekend. That is not the mole I'm talking about here. A stoichiometric mole, a mole in stoichiometry, is similar to, it's similar to one pair. If I say I have a pair, how many things do I have? One pair is two things, right? You have a pair of shoes, you have two shoes. A mole is similar to a dozen. If you have 1 dozen things, how many things do you have? 12. Right? Unless you're a baker. You have 13 in a baker's dozen. So a mole is a quantity like a pair, like a dozen. It's just much larger. 1 mole is 6.022 times 10 to the 23rd things. All right? It's way more things than you ever deal with in your normal life. There's very few things in our regular day-to-day where you need to talk about having a mole of something. The only thing that I can think of is in our walk-in closet, I think my wife has a mole of shoes. But that's about it, right? That's the only normal life thing in my experience. The reason why we need a quantity this large in chemistry is because atoms are very small, all right? Even a small sample of matter with a low mass will have billions and billions and billions, even moles of atoms contained within that sample. So because of the size of atoms, we need a quantity that is so magnificently large. And that is what a mole is. 1 mole is 6.022 times 10 to the 23rd things. Something to keep in mind is sig figs do apply. This number has 4 sig figs. It's also called, just so you know, this thing has a name. It's called Avogadro's number. And I would definitely recommend adding it to your equation list for your exam. All right. Now, why is the mole important? Now that we know what it is, why is it important? Well, turns out it's connected to the periodic table. If you look up carbon on the periodic table, and you look up the atomic mass, right? The atomic mass for carbon is 12.01 AMU, right? AMU stands for atomic mass units, and that's the unit of all of the atoms on the periodic table. Now, here's the deal. We've talked about AMU before. We've introduced it. But I never told you really what it was, like where it came from. I just said it's atomic mass units. Turns out that AMU, atomic mass units, have an alternate formulation. Um, 1 AMU is equal to 1 gram per mole. The unit AMU is the same unit as grams per mole. What is that? What are we talking about? We're talking about a ratio. You could write, instead of 12.01 AMU, you could write 12.01 grams per mole. What this means is that here, in 12.01 grams of carbon, there are 1 mole of carbon atoms. All right, in 12.01 grams of carbon, there are 1 mole, which is 6.022 times 10 to the 23rd, 1 mole of carbon atoms. It also means that a 1 mole sample of carbon atoms has a mass of 12.01 grams. All right, this tells you, the atomic mass tells you how many grams are in 1 mole, and it also tells you the mass of a 1 mole sample of carbon. Here's what this knowledge affords us. This knowledge allows us to solve problems like the following. How many atoms are contained in a 5.00 gram sample of carbon? Right? How many grams are contained within a 5.00 gram sample? Sorry, how many atoms are contained within a 5.00 gram sample of carbon? This is a unit conversion problem, like we've never seen before. All right? We're given that we have 5 grams of carbon. We want to know how many atoms. Now, there is no direct unit conversion to go from grams to atoms. We do know how to convert from grams to moles. That's with the atomic mass on the periodic table. And then Avogadro's number tells us the number of atoms in moles. So this will be a 2-step unit conversion problem. First, we want to cancel grams of carbon. So we put that in our denominator, and we want to convert this to moles of carbon. Put that in our numerator. This unit conversion we look up from the periodic table. The periodic table tells us that a 1 mole sample of carbon will have a mass of 12.01 grams. All right, so this part right here this comes from the periodic table. You look that up. Next, so you'll notice grams of carbon cancel grams of carbon. Next, we want to convert from moles of carbon to atoms of carbon. And 1 mole has how many things in it? 1 mole has 6.022 times 10 to the 23rd things, and that will always be the same. So this unit conversion is Avogadro's number. You want to have Avogadro's number written down on your equation sheet. For the other conversion, you get it from the periodic table. Moles of carbon cancel moles of carbon. And now we need a calculator to crunch some numbers. All right, so let's see. We have 5, let me clear this out, 5 divided by 12.01 times 6.022 times 10 to the 23rd. All right, my calculator is telling me that my answer is 2.507774 times 10 to the 23rd. Let me just double check that. Yep. Now, sig figs wise, I'm limited to 3. I've got 3 there, 4 here, 4 here. I've got to roll with the smallest. So I got to round to 1, 2, 3 sig figs. 7 is going to round up. So my answer with the correct sig figs will be 2.51 times 10 to the 23rd. And then my units are right here. My units are atoms of carbon. All right, that is the number of atoms contained in a 5-gram sample. All right. Let's take a look at the next example. All right, next example is what is the mass of 4.16 times 10 to the 24th atoms of oxygen? All right. Now, this is the same problem, just in reverse. So here, we're given the quantity in atoms, and we're asked to find what mass this has. Now, there is no conversion to go from atoms to grams or from grams to atoms. But we can go from atoms to moles. And the periodic table allows us to go from moles to grams. So we put atoms of oxygen in the denominator, moles of oxygen in the numerator, and atoms of oxygen cancel atoms of oxygen. Next unit conversion, we need to convert from moles of oxygen to grams of oxygen. And this you look up on the periodic table. The periodic table tells you that oxygen has an atomic mass of 16.00, and we know that that means that there are 16.00 grams in 1 mole. Moles of oxygen cancel. Grams is the only unit left standing. We're ready to crunch our numbers. So let's see, 4.16 times 10 to the 24 divided by 6.022 times 10 to the 23rd times 16.00. So my calculator's telling me that my answer is 1.1052806 times 10 to the second power. Sig figs wise, we got to go with our fewest. 16.00 has 4. Avogadro's number has 4 sig figs. My initial amount of atoms, however, only has 3. So I count off 1, 2, 3. 5 rounds up. So this will be 1.11. And my units are gram. Oh no, sorry, 1.11 times 10 squared grams of oxygen. Conversely, your calculator may be telling you that 1.11 times 10 to the second is 111 grams of oxygen. That is also correct. Both of these have the same number of sig figs, same value, same units. So they're both correct answers. All right, now are you ready for a twist? I'm going to write the next example on the board, but we're not going to do it till lecture next week. So I'll write it up for you. You can try this over the weekend. So give this example a shot. Determine the number of molecules in a 2.0 gram sample of ammonia and H3. All right, so give this a shot. This is where I'm going to call lecture for tonight. We'll be back at it. We'll start with this example on Tuesday of next week. So I'll see those of you who have lab tonight. I'll be live on lab. Hit me with your questions. If you don't have lab, have a good weekend. Give this problem a try. We'll come back and do it Tuesday. Later, dudes.